Now we're going to get a little more technical, introduce some equations. If you haven't watched the video on an intuitive introduction to econometrics and the other video, an intuitive introduction to multivariate regression, you should watch those first. Remember, as we go through this, the main idea, even as we add equations, is that we're really trying to compare two things that are the same on a few different dimensions and alter one thing. In other words, we're going to hold things constant. Okay, so first we're going to start with a big looking equation with x's and y's, but we'll jump into some examples as soon as possible. So the population equation looks something like this, and these things are called betas. They look like b's, but they're called betas. And note, we don't put a multiplication symbol between them because it's algebra type stuff, but this is really, this whole thing just says beta 1 times x1. So the y, that's a dependent variable. All the x's are the things that we think affect y. And then the betas are multiplied by the x's, so they're the effect that that x has on the beta. Again, this will become more concrete as we move forward. So another way to write this is there's really an I here for some of these things, and n is the total people in the population. So these things with i's are different for each person in the population. So each person has a different dependent variable, that y. Each person has a different x value. Each person has a different, this epsilon, this e looking thing at the end. That's the error term. They all have different things, but they have the same betas, these b looking things again. And again, it'll become more concrete as we have an example. So there's really only 4 parts to this equation. Here it summarizes: y is a dependent variable, x are the independent variables, variables we think that affect our y. Coefficients, this is how much that x affects y in what direction. And importantly, for multivariate regression, it's holding the other x's in the regression constant. And the error term, these are any other factors for that person or that firm that affect y that we did not include in the model, that we couldn't get for variables. So let's make this a more tangible example. Suppose that we believe a person's education, age, their gender, and how many hours they work affect their wage. We'd have an equation that looks something like this. So let's suppose this is wage per week. We think years of education would affect it. Their age, how old they are. 1 if they're a woman, 0 if they're not. And average hours they work. And then this includes everything else. This would include ability, anything else that you think affects wage plus some randomness. And then this beta 1 will be how much education affects wage, holding the person's age. How much education affects wage, holding the person's age, whether they're a woman or not, and average hours of work constant. So going back to our x and y equation, we are going to take the population equation and write a sample equation. So in introductory stats, if you took that course, talk about how you can't get the population mean, and you have to estimate what the sample mean. So just like we can't get the population mean, we can't get the population equation, so we're going to estimate it with a sample equation. So a couple differences. Anything that has a hat on it becomes an estimator, and we'll be able to get estimates for it. So we'll have an estimate for our dependent variable. We'll have an estimate for these betas. I haven't talked about this beta 0. We'll talk about that potentially in a future video. So we get estimates for these betas, but the x's will be the same. And again, this would be some of these things would be different for each person in the sample now, or each thing in the sample. It could be a firm as well. So I realize even after people take econometrics, they don't know what a data set looks like. So this is just the first top of the data set. That's what those dot dot dots are. So using our example from before and thinking about that population equation we wanted to estimate, the first 4 observations in a data set, there's someone named Lucia who's wage, I guess this is hourly wage, is $23 an hour. They have 16 years of education. They are a woman, and the average hours of work is 0. So that's probably a typo. So we probably want to have like 10, 20, 30, 40 in there. Second person in the data set, their average wage is $14 an hour, 12 years of education, etc. So we have a bunch of different things. In this case, people are things, and we have variables, various variables for them. Most regression analysis would have more variables. So how the sample equation from our example, the one we just saw a data set for, and the one we previously saw the population equation would look like is we'd have an estimate or an estimator for wage. Our betas would have hats. And the most important thing we'll be looking at are these beta hats. So when these become numbers or when they become estimates, they move from estimators to estimates, it might look something like this. And so if this was weekly wage, I think I keep jumping back and forth between hourly wage and weekly wage, but let's say this is weekly wage, and we wanted to interpret this 100. Before we did that, we would want to see if these things were statistically significant, which we'll talk about later. But assume they were. This would say for each additional year of education, if education increases by 1 year, wage will increase by $100, assume it's in dollars, holding the person's age, whether they're a woman or not, or average hours of work constant. So another way to explain that I think is more intuitive is if we compare two people who are the same age, both are either women or not, and both have same average hours of work. If one has 1 more year of education, they will have $100 more in wage. If they had 2 years more of education, they'd have 200 more years of age. So going back to an example from a previous video, we looked at how coffee consumption affects miscarriage. So originally people looked at a correlation, which you could just run a regression with one variable in it, and this would give you some type of correlation. It wouldn't give you the correlation coefficient exactly, but it would tell you whether coffee consumption and miscarriages was positively related. But then we talked about how it might make sense to control for age and nausea. So now this beta 1 tells us if two people are the same age and have the same nausea level when they are pregnant, the beta 1 will tell you how much drinking coffee will increase or decrease miscarriages, or maybe not much of an effect. And the sample equation, we just put hats on it. This needs a hat as well. On the betas, but not the variables. Thanks again for listening till the end.